So can you see the screen?
Yes, sir.
Yes, sir.
Okay, so it's visible. Okay. Uh, See, in the last class, we were discussing about the boundary layer equations for the parallel flow over a flat plate, and we have considered a laminar flow, okay, over the flat plate, and we discussed about the continuity, momentum, and energy equation. I told you don't need to remember these equations, but you should have some idea about the significance of the various terms actually. Okay, and then finally, I told you when we consider a flat plate, these are the results. Okay, results means we discussed about the continuity equation, we discussed about the momentum equation, we discussed about the energy equations, and I told you from the first two equations, that is continuity and uh, momentum equation, we can get the value of the we can define basically the velocity boundary layer and the solution of this thermal boundary layer can be achieved with the help of the energy equation. Okay, so and finally when we solve these equations, we get the velocity boundary layer thickness, which is equal to delta, and the value is equal to uh, 5x divided by Reynolds number, square root of Reynolds number, or local Reynolds number. So when we say x, it is the local Reynolds number. We calculated the value of the local shear stress. The local shear stress is given as 0.664 local Reynolds number raised to power minus 1 by 2. Okay, and similarly, when we calculate the Nusselt number, this is the local Nusselt number, which is given by hx into x divided by k. Okay, I will define it once again today. So the value comes out to be 0.332 Prandtl number raised to power 1 by 3, Reynolds number, local Reynolds number raised to power 1 by 2. And I told you that this particular relation is valid for when the Prandtl number is approximately equal to zero point 0.6 or greater than this particular value. Okay. Moreover, one more important thing that I wanted to remind you is that it is valid for laminar flow, means all these correlations, and the plate is isothermal flat plate because means the temperature at each point on the flat plate is same actually. Okay, and when we have to calculate the values of various parameters, like if we are calculating the local Nusselt number, we need to calculate the value of thermal conductivity. For example, if I talk about Prandtl number, it is given by mu Cp by K. Okay, so we have viscosity, specific heat, and thermal conductivity involved in it. For example, if I am talking about Reynolds number, it is given by rho u infinity into x divided by mu. So rho comes into picture. Okay, so all these properties, when we are calculating, we will have to calculate it at a film temperature. TF stands for the film temperature, and that film temperature is equal to the sum of surface temperature plus free stream temperature divided by 2. So it's basically the mean temperature which we are calculating. Then comes the thermal boundary layer thickness. So thermal boundary layer thickness is given by delta, which is the velocity boundary layer. This is velocity boundary layer. Okay, and this is thickness of the thermal boundary layer. Thermal boundary layer thickness, and the relationship between these two is that delta is equal to delta T is equal to delta divided by Prandtl number raised to power 1 by 3. And it's very clear from here that if we have a particular gas for which the value of Prandtl number is approximately equal to 1, in that particular case, the thermal boundary layer thickness will be equal to the velocity boundary layer thickness. And there can be certain cases, for example, in case of air, the value of the Prandtl number is for air, the value of Prandtl number is somewhere lying between the range of zero point 0.7 to 0.6 to zero point 0.7. Okay, depends upon the temperature at which we are calculating the Prandtl number. So in case of air, we can say that the value of the Prandtl number is approximately equal to 1, and in that particular case, the boundary layer thickness and means velocity boundary layer thickness and the thermal boundary layer thickness will be same. Okay, so means here we have calculated two relations. One is for the local friction coefficient, and another is for the local heat transfer coefficient or local Nusselt number correlation. Uh, okay, so once again, these are the various uh, terms: velocity boundary layer thickness, local friction coefficient. Same equations are written here. Only thing is, I am showing you again and again so that you are in a position to remember them. Okay, that is the only reason. Now, here what I am trying to do is, here we have the this is the value of the local friction coefficient, and it is given by this particular relation 0.664 local Reynolds number raised to power 1 by 2. Now, this value is for a particular location actually. Now, suppose if I say that uh, this is the plate actually, okay, and I say that I am calculating this value of friction factor or coefficient of friction at this is x is equal to 0, and let us say this is x is equal to x. So I am calculating at this particular point. Rather, I can say also that this value is actually L. Okay, so it is the uh, trailing edge at which I have calculated the coefficient of friction. Okay, so what I can do is I would also I am also interested in calculating the average friction coefficient for the whole length of the plate. Okay, so this is this is actually average or mean value of the average uh, coefficient of friction, average coefficient of friction for the whole plate. So that value will be given by, I can take this is the local value multiplied by dx, and I can integrate this from 0 to L and divide here by L. So I will be able to get this average friction coefficient for the whole plate. So basically I have tried to calculate this value of friction factor for the whole length here. Okay, if I consider any particular small thickness where I have calculated this value of CFX, suppose here, and multiplied it by dx and integrate it from 0 to L and then divide the total value by L. So I will be getting the average value here. Okay, so what I can do is I can put this value of CFX here. So the value of CFX comes from this particular equation. Okay, so it is equal to 0.664 rho u infinity x divided by mu, because this is the Reynolds numbers definition. Okay, so here I have to use dx also. Okay, so this also is to be taken into consideration, which I have missed out. And then you can see this L is constant, rho is constant, mu infinity and u infinity and mu, all these parameters are constant. Only variable is x raised to power minus 1 by 2. So we can integrate it, and you can see this integration, or you can do it yourself. And finally, what you will find here that this CFL, okay, so this is the average when I am putting a bar here. Okay, this is a sort of bar here. So bar here means that I am calculating the average value of the friction coefficient, and this L shows for the whole length of the plate. Okay, so naturally you can see it here. Here in it comes L. So here the Reynolds numbers is now for the whole length of the plate. It comes into picture. So I can say that this value of CFL, okay, coefficient of friction for the whole length, comes out equal to twice the value of the local friction coefficient at a location where x is equal to L. So here this is the value of x actually. So this is local friction coefficient at the trailing edge. So this is very very important to understand. Otherwise, you may lose the track. So I can also write this equation like in this particular fashion. I have written that if I am considering the part length of the plate, suppose this is the plate, okay, and the length is L. but I am calculating the value I am interested in calculating the value of the average heat transfer coefficient, average local skill friction coefficient for the length x. Then at this particular x location, this is the x location here. This is the value of the local friction coefficient, and if I am calculating the average value for the length from x is equal to 0 to x is equal to x, then that value will be twice of the value of the friction coefficient which is existing at location x. So that is what is required here. I have shown it here also. You can see here cfx is here, means at this particular location, and average value of cfx is for this whole length from here to here. Okay, so that is what you need to remember. Now, similar to this, we have been given with this value, and ux means the local Nusselt number is given by this value. This we have got this particular equation for the flat plate for Prandtl number greater than zero point 0.6. We can also prove here that Nusselt number will be equal to twice the Nusselt number or the local Nusselt number at the trailing edge. Okay, so that is average Nusselt number at x is equal to L is twice the local Nusselt number at x is equal to L. Here x is equal to L means I am considering the full length of the plate. So once again, if this is the full length of the plate, okay, so I am calculating the average Nusselt number here, and this is the value of the local Nusselt number at x is equal to L here. Okay, x can be any location. So this total length is actually L for the plate. So this value is the local value at this particular location only, and this HL stands for the average value of the uh, heat transfer coefficient. Okay, so here I have shown this derivation also. So what I have considered here, I have a flat plate here. Okay, I am considering this small thickness or small elemental strip at a distance x from the leading edge. This is the leading edge, and this is the trailing edge. Okay, so if I have to calculate the value of the q double dash, so it is the heat flux. Okay, it is the heat flux. The unit is watt per meter square. Okay, so what I will write, I will the value of the heat transfer coefficient at this particular location is, let us say, hx. Okay, so I will write this heat flux is equal to hx into delta t, because you know the convective heat transfer, I will write that q is equal to ha delta t, and if I divide it, I will get h into delta t. So basically I am calculating this value of heat flux at this particular location, and if I want to calculate this value of q total heat transfer, then I will have to integrate this particular equation over the total area of the plate. Okay, over the total area of the plate, that is why I have multiplied here by as. Okay, so this value actually can be rewritten as, means here I have used the value of uh, area. So you can say this is the area, this is that small area from where the heat flux is for which the heat flux has been considered, means the area at of small strip multiplied by the local heat transfer coefficient into delta t. Okay, and I can integrate this equation from x is equal to 0 to x is equal to L. So this way I can calculate the heat transfer. Other way could be, I have some value of average heat transfer coefficient which is available to me. I can multiply it by the total area here, L into 1, multiplied by the delta t. Okay, so this way means I have made two equations. One is this equation and other is this equation. Okay, here I am considering the average heat transfer coefficient multiplied by the total area multiplied by delta t, and that should be equal to this value of the q. Okay, so you can see it here. uh, I have taken this value in the integration here. So finally what do I get is, I get uh, you will see it here, it is h bar, means it is the average heat transfer coefficient multiplied by this is the area, this is the delta t, and this is hx into delta t into dx, and this is nothing but this particular equation only. This is the equation. So finally, I can put this value of hx from this particular equation, this particular relation which I have got here. Okay. So you can see it here. It is 0.332 Prandtl number raised to power 1 by 3, Reynolds number raised to power 1 by x. Okay. So Prandtl number raised to power 1 by 3. This is the Reynolds number raised to power 1 by 2. And because it was hx I am calculating, so k will go to this side and x will come down. So this term has been introduced here along with the when we are writing the value of hx multiplied by dx. So you can see it here. Finally, this uh, then I can see that there are certain terms like this 0.332 Prandtl number and this value rho u infinity into mu. This is a constant. Then k is also a constant. So this can be taken out of the integration sign except the value of x. So you can see it here. I have written it all these values. K I have taken to the left hand side here. And then when finally I integrate all these terms, so this is the final answer that I get. And finally, I get the Nusselt number, which is the average Nusselt number for the whole length is equal to 0.664 Prandtl number raised to power 1 by 3, Reynolds number raised to power 1 by 2. And this value is actually, if you see this particular equation, which is given here in the top, so you can see it here. This is actually Nusselt number uh, at the trailing edge, okay. So this is the local Nusselt number, local Nusselt number, okay. So I have written it here, local Nusselt number at L, that is trailing edge, and NUL is the average Nusselt number for the whole length of the flat plate. Okay, so let us proceed further. So this is how I have tried to show the variation of the heat transfer coefficient. So you can see it here, this line, if you, this is the heat transfer coefficient. So if you see here, this is the local value of the heat transfer. So if this is the length of the plate, you can see it, what is happening to the heat transfer coefficient. So here x is equal to 0 and here x is equal to L. And this curve shows the variation of the heat transfer coefficient, local heat transfer coefficient, and you can see it is reducing. This I have already explained why it is reducing. And if I am calculating the average value, then this is the average value. Okay, this is the average value of the heat transfer coefficient over the whole plate. So that is what we have calculated here in this particular relationship. Okay, so I hope this must be clear. Then let us proceed to the different non-dimensional, dimensionless or non-dimensional numbers or parameters. See, you have seen we have been using certain numbers here. For example, Reynolds number, Prandtl number, and Nusselt number. And there are many more numbers which are used in heat transfer, or rather convective heat transfer. So these are important here. So Reynolds number, you know, it is the ratio of inertia force to the viscous force in the velocity boundary layer, and it is used in forced convection, and it is approximated as Reynolds number is inertia force divided by viscous force. And you know, when we write these values, you will get mu infinity into LC divided by nu. So nu is dynamic viscosity divided by density, and here it is kinematic viscosity written. So this is the definition. This LC stands for the characteristic length. You know that if it is a plate, this characteristic length will be L. So LC will be equal to L in case of flat plate, and LC will be equal to diameter in case of a tube flow. Okay, so I can write it here. So for a flat plate, LC is equal to L, and for a tube, LC is equal to D. And other things are already known to you about mu infinity. U infinity is the free stream velocity, density, dynamic viscosity. This is kinematic viscosity. And one important thing which you can see it here is it characterizes the type of flow, whether it is laminar or turbulent. So Reynolds number is used for that particular case. Now let us talk about the critical Reynolds number. This is also very important. We discussed about it. Uh, uh, It is the value of the Reynolds number where the boundary layer changes from laminar to turbulent. Okay, and it is denoted by Re critical. So for a flat plate, the transition from laminar to turbulent boundary layer occurs roughly when the critical Reynolds number is this value means greater than 5 into 10 raised to power 5. And for tubes, the critical value of the Reynolds number means from for transition from laminar to turbulent boundary layer occurs when the Reynolds number based on diameter. So if we are using D, that means we are calculating for the pipe. So mu D by nu, this value is greater than 2300. So I would like to clarify it here. The moment the geometry changes. For example, we are considering a flat plate. Okay, so the characteristic length is L. If we are considering a pipe flow, the characteristic length is T. And sometimes we take different types of shapes also. For example, if it is a square tube or a rectangular tube through which the flow is taking place, so we will have to consider different value of the characteristic length. And for example, there can be flow over the cylinders also, flow over the spheres also. So we have to take the appropriate value of the characteristic length, and in each of these cases the transition from the laminar to turbulent boundary layer occurs at different values of the Reynolds number. Right now we are only talking about the flat plate and the tube flow. The moment it is the flow over the cylinders or say over the sphere, according to the geometry, the value of the critical Reynolds number will vary. So if somebody asks you in some interview or some uh, YOC that what is the value of the Reynolds number, uh, critical Reynolds number for transition from laminar to turbulent in case of a flat plate, so the value is different than 2300. 2300 is for the pipe flow only. These are generally accepted values of critical Reynolds number, which may vary with surface roughness, level of turbulence, and variation of pressure along the flow. Okay, so it is not necessary that this is a single value at which the transition will take place. The value is in a particular range, but these are most accepted values. Means corresponding to this value, you can always consider that flow transition has already taken place. Okay, so the next one is the Prandtl number. Now, this is a very, very important number. I have discussed about discussed about it earlier also. It is defined as the momentum diffusivity to the thermal diffusivity alpha. So momentum diffusivity is defined as nu. Okay. So basically, suppose we have a flat plate here. Okay. And there will be two types of the boundary layer like this and this. So let us say that this is the uh, thickness of velocity boundary layer, and this is the thermal boundary layer delta T, and this is the flat plate. Its surface temperature is Ts, and the fluid is approaching it at a velocity u infinity, and its temperature is T infinity. And we can say that T infinity is less than Ts, or otherwise it could be Ts is greater than, or sorry, T infinity is greater than Ts. So anything can happen in this particular case. So it is basically showing us, this Prandtl number shows us that how much is the diffusion of the momentum from the surface of the solid to the free stream, and how much is the diffusion of the thermal, means thermal energy. Okay, so it is showing the relative measure of two. So you can see it here. Uh, if you calculate the momentum diffusivity and thermal diffusivity, it is mu by alpha. Mu can be written as nu can be written as mu divided by rho, whereas alpha can be written as k upon rho Cp. So this is for k is for the fluid. So finally, this is the expression for the Prandtl number mu Cp by k. You can see it here. It is a dimensionless property. It is a function of temperature. It provides a measure of relative effectiveness of momentum and energy transfer in the velocity and thermal boundary layers respectively. So this is very, very important. So for gases, Prandtl number is approximately equal to 1. That is both momentum and heat diffusion through the fluid takes place at the same rate. And when this is the condition, if you will draw the velocity boundary layer and thermal boundary layer, they will be overlapping each other. If this is the thickness of the delta, then I will say the delta T is also on the same line. Okay, delta T is also here. So it is either delta or delta T, both. Now the second case, if we have the liquid metals, in case of liquid metals, if you will calculate the value of Prandtl number, it will be very, very less in comparison to 1. So what does it shows? When the Prandtl number can be less. See, Prandtl number is given by nu by alpha. So if the value of alpha is very, very large, in that particular case, the value of Prandtl number will be very, very small than 1. So in that particular case, the thermal boundary layer, because you can see alpha is depending upon the thermal conductivity. So thermal, if the thermal conductivity is high, then the value of alpha will also be high. So it means the heat transfer into the boundary layer or heat transfer into the fluid will be at a large rate actually. So in that particular case, we will say that this is the value of delta, okay, and this is the delta T, means the thermal boundary layer will be thicker in comparison to velocity boundary layer. So it actually means delta T is large in comparison to delta. Whereas if we talk about uh, 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 I think it's written here or no. Okay, let me read it first of all. Consequently, the thermal boundary layer is much thicker for liquid metals and much thinner for oils. Okay, for oils, the velocity boundary layer is as shown in figure 7.6. So 7.6 is not here. I will tell you. Further, the thickness of two boundary layers can be related at as this parameter. So I have already told you delta T is equal to delta divided by Prandtl number raised to power 1 by 3. This I explained you. So okay, this was in case of flat plate, but if it is not a flat plate, then this n exponent will come into picture. Okay, so I will also tell you about, just a minute, I will introduce a slide here. So now for example, if the Prandtl number is greater than 1, what will happen in that particular case? So we will have a flat plate here. Okay, when I say Prandtl number is greater than 1, it means the value of Prandtl number is equal to nu divided by alpha. So if the value of nu is large, in that particular case, this value will be greater than 1. So it means the the diffusion of momentum is at a larger rate, okay, because nu represents the momentum diffusivity. So in that particular case, this will be the velocity boundary layer. Okay, this is the value of delta, and you can say this is the value of delta T. Okay, so thermal boundary layer will be smaller in this particular case when the Prandtl number is very large. So delta is very, very large in comparison to delta T when the Prandtl number is greater than 1. So that is how we interpret this Prandtl number. So Prandtl number is a very, very important number. Now let us look at the Grashof number. Before the Grashof number, I will come to the Nusselt number actually. So what is Nusselt number? Nusselt number is defined as the ratio of convection heat flux to the conduction heat flux in the fluid boundary layer, or you can define the Nusselt number as convection heat flux divided by the conduction heat flux. So it is given by H into delta T divided by Kf into delta T by Lc. So you can see here, what is this value? It comes out to be HLC divided by Kf. So we discussed about this number in the practical of force convection also, and I have explained it to you there also. So it is nothing but it is basically the ratio of heat transfer by convection. So I can say Nusselt number is also can be written as Q convection divided by Q conduction. Okay, so either you use this definition or you can also call it as the convection heat flux divided by conduction heat flux, because area will cancel out when we are saying heat flux actually. So it will come out to be HLC upon KF. So where delta T, if you write, is the temperature difference between the wall surface and the fluid. Okay. H is the heat transfer coefficient. Kf is the thermal conductivity of the fluid. Lc is the thickness of the fluid layer. Okay. Uh, and based on the interpretation, the value of Nusselt number as unity indicates that there is no convection. The heat transfer is by pure conduction in the boundary layer. So this is about when Nusselt number is equal to unity, that there is no convection, but the heat transfer is by pure conduction. So we need a value of Nusselt number which is very very large in comparison to 1. So if it is equal to 1, that means there is no convection taking place in the fluid. So you can read it here, large values of Nusselt number indicates large convection in the fluid. So these three numbers, which three numbers? One is the Reynolds number, other is the Prandtl number, and other is the Nusselt number. These three numbers are important in forced convection. Okay, these are important in forced convection. Why these are important in forced convection? You have seen that local Nusselt number equation that you got was equal to 0.332 Prandtl number raised to power 1 by 3 into local Reynolds number raised to power 1 by 2. So basically, uh, these three non-dimensional numbers are giving us the value of the heat transfer coefficient in case of forced convection. So that is why these three numbers are used in forced convection only. Now let us move to the Grashof number. Now what is Grashof number? Grashof number is defined as the buoyancy forces to the viscous forces. Okay, buoyancy to the viscous forces. You know that it basically relates to the phenomena of natural convection or the free convection. So Grashof number is related to the free convection actually. Okay, free convection or natural convection. Like in case of forced convection, we calculate the value of the Reynolds number and we identify whether the flow is laminar or turbulent. Similarly, in case of free convection or the natural convection, it is the Grashof number represented as GR, which is telling us whether the flow is laminar or turbulent. So, in free convection, Grashof number will help us. So we can see its definition is the ratio of the buoyancy forces to the viscous forces acting in the fluid layer. It is used in free convection and its role is same as that of the Reynolds number in the forced convection. The Grashof number characterizes the type of the boundary layer developed in the natural convection heat transfer. It is denoted by GR and is expressed as, so this is the value of GR, which is G beta delta T LCQ. Once again here LC is some characteristic length and this is nu square. Nu means kinematic viscosity square. So this is the definition. It is the ratio of buoyancy forces to the viscous forces. Okay, because the velocity boundary layer or the flow of the fluid in case of natural convection is because of the buoyancy forces. Okay, so we are taking that into consideration with respect to the inertia forces. So where g is the acceleration due to gravity, beta is the coefficient of volumetric expansion, and it is given by 1 by tf. Okay, 1 by t. Sometimes you can say it is 1 by t. T here is to be taken in Kelvin actually. And delta T is the temperature difference between the surface and the fluid. And if you say TF, TF is what? TF is the surface temperature multiplied plus fluid temperature divided by 2. So it is the average of the surface temperature and the fluid temperature. Other things are written here. And for free convection, the transition from laminar to turbulent occurs when critical Grashof number is 10 raised to power 9. So that is the value of the Grashof number. But I will say, uh, you can see it here when we talk about the value of LC, which is the significant length of the body or characteristic length of the body in meter. So it is height L for vertical plates and cylinders, okay, and diameter D for horizontal cylinder and sphere, whereas it is equal to AS, surface area, divided by parameter for other geometry. So that you need to remember, and This is the distinction, means the value of the Grashof numbers approximately equal to 10 raised to power 9 represents the transition from laminar to turbulent in natural convection. So the next one is the two, three more numbers are there. One is the Stanton number. Now, what is Stanton number? It is the ratio of heat transfer at the surface to the transported by fluid by its thermal capacity. Okay, so it is heat flux to the fluid, or it is basically convection heat flux divided by heat transfer capacity of the fluid. So rather than the definition, you can also call it as a non-dimensional heat transfer coefficient. Stanton number is known as non-dimensional heat transfer coefficient. Okay, so Stanton number is nothing but it is the non-dimensional heat transfer coefficient. So you can see it here. It is coming out to be H over rho Cp U infinity. So when you will try to find out the units, there are no units actually. So it's a non-dimensional heat transfer coefficient. Okay, so that is the value of the Stanton number. Or mathematically, it is the ratio of the Nusselt number and the product of Reynolds number and the Prandtl number. So you know that there was a relationship between Nusselt number and Reynolds number and Prandtl number when we derived the uh, uh, when we solved the uh, uh, three equations of continuity, momentum, and energy equations, and then we found a relationship between Nusselt number, Reynolds number, and Prandtl number. So basically, Stanton number is nothing but it is the local Nusselt number divided by local Reynolds number into Prandtl number. Okay, so the Prandtl number value doesn't vary with the location because it is the ratio of mu Cp by K. Okay, what is it? Mu Cp by K. So this is not going to vary, whereas the Reynolds number and Nusselt number, they are dependent upon the location. So this is the sort of Stanton number is a sort of non-dimensional heat transfer, local heat transfer coefficient here in this particular equation. So we can also calculate the value of the average Stanton number. Okay. Now let us talk about the Peclet number. Peclet number, it is the ratio of heat transfer by convection to heat transfer by conduction. Very, very similar to what you say, a Nusselt number actually. It is denoted by P and is expressed at heat transfer by convection divided by heat transfer by conduction. And you can see it here. It is convection means mass flow rate into specific heat to delta T, and here by conduction it is K into delta T by L. So this is conduction part, this is convection part. See, these numbers are quite similar to each other. It is defined according to the situation. Okay, so this is the final value of the Peclet number. It is the product of Reynolds number and Prandtl number. So Peclet number is Reynolds into Prandtl number. So you can always say that Nusselt number is a function of Peclet number. Nusselt number is a function of Peclet number. Sorry. So the next one is the Grates number. It is the ratio of the fluid stream thermal capacity to convective heat transfer, and it is denoted as GZ and represented as thermal capacity of the fluid divided by the heat transfer by convection. So where it is important, that is more you should know that actually generally it is associated with thermal entry length of a fully developed flow through tubes. Okay, so we have not discussed about the tube flow till now, but actually what happens, like in case of uh, flat plate, we are not talking about any entry length, but in case of pipes, okay, for example, if this is a pipe here and we want, there is some fluid which is going, entering here with the free stream velocity u infinity, you know, there is a particular length of the pipe till the flow is not fully developed. So after this particular length, this is known as x entry. So it is the entry length. Okay. And after this, if you will see the velocity boundary layer, that would be perfectly um, um, developed actually, and like this. Otherwise, if you take any other section here, so it could be something like this. Okay, so at the center it is not fully developed, and if you will take at the entry, so the profile will be like this, straight profile, okay, with a vertical straight line like this. So as the flow enters into the pipe with the as the length increases, the velocity layer also, velocity profile also develops. Okay, and it becomes parabolic when it is fully developed. So this is parabolic velocity profile. You must have studied it in fluid mechanics course. So the length after which the profile is fully developed, that length is known as the entry length, and this number is related to that particular condition. So it is equal to Reynolds number into Prandtl number into d by x, and where this x is hydrodynamic entry length. Okay, so you should remember it. Now, yeah, these were some of the numbers which we discussed. Okay, these are very, very important, whether you are appearing for some competitive examination or maybe for some viva voce. So these are very important. So now there are some numerical problems. Okay, two, three numerical problems I have taken so that you can understand the uh, means topics which we have studied till now. So first one is forced heat convection on a heated horizontal plate. The local heat transfer coefficient may be expressed as h as a function of x is equal to some constant into x raised to power zero point 0.5, where x is the distance from the leading edge of the plate and c is a coefficient independent of x. So you obtain an expression for h average heat transfer coefficient divided by the local heat transfer coefficient, because you can see here is a bar over the head of heat transfer coefficient. So it is average, where this value is the average heat transfer coefficient between the leading edge and the location x. So what we can do is, we can always calculate the value of the average heat transfer coefficient as uh, 1 by x integral 0 to x h x into dx. Okay, so that is how we can calculate. This is the relationship. This I have explained you earlier also. So you just have to put these values here. You can put the value of hx here. Hx is given by c x raised to power minus 0.5 dx. So c is constant, can be taken out of the integration sign. And here this x, you should not confuse why we are not considering it for integration, because this is the total length. So this total length is constant actually. So this cannot be integrated. Okay, mind it, because we are trying to calculate the heat transfer coefficient for this length of the plate x. Okay, so this length has a particular value. Okay, so the heat transfer coefficient is varying with respect to x raised to power minus 0.5. So when you will calculate, you will find that this ratio comes out to be 2. And I have already told you in our calculation, when we got the solution of the boundary layer equations, we have seen that the average heat transfer coefficient is equal to twice of the local heat transfer coefficient. Okay, this was the relationship which we got earlier also, and the same thing comes here. But don't go directly to the final answer, because here the value of x is minus zero point 0.5. Had it been minus 0.7, the answer would have been a different answer. Okay, so don't go directly to the conclusion that the final average value will be equal to twice the local value. It will depend upon the correlation which we are using. Now there is a thin plate of 1 meter long, 1 meter wide, placed in airstream, moving with a velocity of 2.5 meter. Determine the type of the flow over the plate. So we just have to calculate the value of the xc divided by mu. So xc is the critical length. So if we are in a position to calculate the value of the critical length, then we can understand what type of flow will be occurring over the flat plate. So we can put all the values. I think what is not mentioned here is, yeah, yeah, because air is considered, but its temperature is not mentioned here in this particular problem. So we need the value of temperature also, so that corresponding to this particular value of temperature means uh, either the property should be given or temperature of the surface as well as the temperature of the free stream should be given to us. When these both temperatures are given to us, we can calculate the value of Tf. So Tf will be equal to Ts plus T infinity divided by 2. And then for air, the tables are given at the back of every book. If you are using any book of heat transfer, you can go to the tables for the air, and corresponding to this value of Tf, you can calculate the value of rho, you can calculate the value of mu. Okay, find out the value of these two values from the table, and then you can put it here. So this is these values have been taken here, and uh, or this may be the value of mu, this is the value of rho, this is the u infinity, and this is the critical value of the Reynolds number. So from here you can calculate the value of xc. So xc comes out to be 1.52 meter. So it means this plate is only of length 1 meter. Okay, whereas the transition will take place at a distance of 1.52 meter. So naturally the flow is laminar over this flat plate. So this is another question here. Air, yeah, I think, yeah, this is a different question. So air is at a temperature 20 degrees Celsius flowing over a heated flat plate at 143. So this is the surface temperature, and this is the value of T infinity. Okay, and the velocity U infinity is given as 3 meter per second. The plate is 2 meter long, so that means this is the value of length, and 1.5 meter. So this is the width. Calculate the thickness of hydrodynamic boundary layer and the skin friction coefficient at 40 centimeter. So we have been given a value of x which is equal to 40 centimeter, corresponding to which we have to calculate the value of delta, and skin friction coefficient means local skin friction coefficient. These two values we have to calculate at x is equal to zero point 0.4. The kinematic viscosity of air at 20 degree may be taken as this value. Okay, so because it is given in the question, so we can take this particular value directly. Otherwise, when we have to calculate the properties, we will have to take the average values. Okay, so you should always go for the calculation of the properties corresponding to Tf, which is equal to Ts plus T infinity. So here I think it has been wrongly done in this particular case. So 40 centimeter is the value of x. So we can calculate the local Reynolds number, u infinity into x divided by nu, and this value comes out to be 7.9 into 10 raised to power 4. So it is less than the critical value of the Reynolds number. This is R E critical. So that means the flow is laminar. So that's clear. So once the flow is laminar, we have calculated the value of delta. We know that delta is given by 5 times x divided by the Reynolds number, local Reynolds number square root. So you can put all the values, and finally this is the uh, thickness of the velocity boundary layer, and the local skin friction coefficient is given by this particular equation. I have told you it is equal to CFX equal to 0.664, Reynolds number local raised to power minus 1 by 2. So here Reynolds number is taken in the denominator. So this is the local skin friction coefficient. So quite easy, you can calculate it. Similarly here, they want the value of the local heat transfer coefficient at 0.4 and heat transfer from the first 40 centimeter of the plate. So from first 40 centimeter of the plate, we also have to calculate the value of Q. So yes, okay, so you can see here they are using now this is the value of 77. So that means that particular value can be used for uh, velocity boundary layer. Okay, so for finding out the velocity boundary layer, you can consider this 20 degrees Celsius temperature, which is the temperature of the air. So here you are taking the properties corresponding to 77. Okay, so we can see from the tables rho, Cp, nu, thermal conductivity, and Prandtl number. All these values will be given for the air, which you can see from the tables, and this is the value of x. So we can calculate the value of the critical Reynolds number, which is 5.78 into 10 raised to power 4. and Nusselt number is given as 0.332. Reynolds number is to power 1 by 2, Prandtl number is to power 1 by 3. So we have all the values with us. So from here, we can calculate the value of local heat transfer coefficient. It comes out to be 5.3. So if you have any questions, you can ask me. And then we can calculate the average value. Average value can be calculated. It is, you know, that average value will be equal to twice the local value. Okay. So local value came out to be 5.3. So average value is twice of that. So it will be 10.6 watt meter square per Kelvin. And total heat transfer will be given by Hx into A into delta T. Now there is this is the heat transfer only from one side, so it will come out to be 725 watt because this plate is heated. Okay, this is at 134 degrees Celsius, so heat will be lost from the top as well as from the bottom, from both the sides actually. So that is why we are multiplying it by 2. So total heat loss will be 1450. So I think yeah, this is these were some numerical problems, and now I am just going to this part, determination of convection heat transfer coefficient. See, the method which we have used till now was the second one, and that is the exact mathematical solution of the boundary layer equations. The answers which I have given were based on the second method, which is the exact mathematical solution of boundary layers. Now we can calculate the value of heat transfer coefficient by five methods actually. So what are those five methods? The first one is the dimensional analysis combined with the experimental data. Second, we have already discussed exact mathematical solution. The third is the uh, approximate analysis of boundary layer equations by integral methods. So this was the second method which we used was differential method actually. So you should always remember it is a differential method. We can also choose integral methods, and it will give us approximate results. Okay, it is the approximate analysis. Then we can also go for analogy between heat and momentum transfer. This is in our course, we will do this. And the last one is the numerical analysis. So these are the five methods of calculating or determining the convection heat transfer coefficient. All methods can evaluate heat transfer coefficient, but no single method can solve all types of problems because each method has its own limitations that restricts its scope of application. So this is what you need to remember. So these are the various methods. It is described a little bit about them. Okay, I have already told you about this part. So we will do it also. We will be doing this part and this also. So when we will do it, you would be able to understand it. But approximate analysis, I will not be doing. Okay, it is not in your course. I will be just telling you what we get actually from the approximate analysis. What are the values of the heat transfer coefficient? But we will be going for the exact solutions. Okay, and dimensional analysis also we will discuss actually. So basically four methods we are going to discuss here. Except the approximate analysis, analogy we will consider, and numerical analysis we will not consider. Sorry, numerical analysis we will not consider. It is not in your course. We usually teach it at PG level. So that is what I wanted to tell you in today's lecture. So if you have any questions, you can ask me.